we're going to be talking about how to use the definite integral of velocity to find displacement and total distance. Let's say, for example, I have a definite integral from time 1 to time 2 of the velocity of a particle moving along a line. You might remember that velocity is the derivative of the position, which I'm going to call x of t, and so velocity would be x prime of t. If you integrate x prime, well, you're just going to be at x of t, position, and then using your fundamental theorem, when you evaluate, you will have x of t sub 2 minus x of t sub 1. It's the difference in the positions. So this will give us the change in position, also known as displacement. Change in position, or in physics, displacement. If I'm trying to find the total distance traveled by a particle over a time interval, I'll use the definite integral of the velocity, but I'll need to put absolute value. If you do the absolute value of velocity, you're actually integrating the speed. And so this definite integral will give us the total distance traveled by the particle from time 1 to time 2. Total distance traveled. Let's look at a few examples. Here, we've got a chart. This shows you the position of a particle at various time values. Notice at time 1, our particle is located at 3 on the number line. And then, this is a critical point. At time 5, our particle has traveled to -2. And then, at time 7, it's going to be back here at +5. Alright, so if we do the integral from 1 to 7 of v of t dt, we're actually integrating x prime of t, and so I've said we would have x of t, and then using our fundamental theorem, we'll have x at time 7 minus x at time 1. In other words, we would have 5 minus 3, which is 2. You can see that the change in position from where we started and where we ended up is 2 spaces. That's not the distance we've traveled, though. Look, we've traveled a lot further than that. The problem is that some of our travels were to the left, so in a negative direction. You can see on our number line we actually went 5 spaces to the left, and then we went 7 spaces to the right. So -5 and +7, that's what's resulting in our displacement of 2. If I were, on the other hand, to do the definite integral from 1 to 7 of the absolute value of the velocity, which remember we call that the speed, well, it would make all of this negative movement take on a positive value. So we would have 5 spaces moved. It doesn't matter that it's going to the left. We're going to give that a positive value. And then, from -2 to +5, we've moved 7 spaces to the right. So our total distance traveled is 12 spaces. Let's look at another example. Again, the chart shows us the position at the end point and at a critical point. This time, at time value 2, we're located at 2 on our number line. Then, at time value 4, we're located over here at +5, so we've moved to the right. And then, at time value 8, we are back here at 1. If we were to do the integral from 2 to 8 of our velocity, remember, that's the same as integrating x prime of t. which gives us x of t from 2 to 8, and then x of 8 minus x of 2. Well, let's see. X of 8 is 1, minus x of 2 is 2, so 1 minus 2 is negative 1. Our displacement is negative 1, which means we're 1 unit to the left of our starting point, which is true. We are ending up 1 unit to the left of where we started. On the other hand, if we were to integrate from 2 to 8 the absolute value of our velocity, well, we would get a rightward movement of 3 spaces and a leftward movement of 4 spaces. But we really don't care about the direction. The absolute value makes everything take on a positive value. So we would have 3 plus 4 equals 7. Our total distance traveled is 7 spaces. Thanks for listening and enjoy calculus.